Okay, so today we are going to talk about the minimum spanning tree problem. Okay, or we call it MST, right? So I'm sure you guys would have done this in your course on algorithms, but let's quickly revisit what is an MST, right? So what we are given is a graph. It has vertices, edges, and it's a weighted graph. So W basically gives you the weights on the edges. And what we are interested is in an MST. So what is an MST? It's basically a subgraph of G that is connected, right? And it spans G. What does it mean to span G? That means all the vertices are covered. V of T is the same as the V of G, right? So the vertices, it covers all the vertices of G, and it has minimum weight, right? What is weight? So I'm going to call this MST. Let me denote it by T, okay? So T is basically the subgraph we are talking about. And the weight of T is nothing but the sum of the weights of all the edges in T, right? So E belongs to the edges of T, right? So that's the minimum spanning tree problem. So I hope you guys recall this from this definition. Okay, basically it's the tree which spans all the vertices, and it also minimizes the total weight of that tree, right? So it will have exactly n-1 edges if n is the number of vertices, right? You don't need to argue that it's a tree really, right? This definition suffices because you're looking for minimum weight. So you can argue that, you know, if you have something other than a tree, you can reduce it to a tree, right? Okay. The algorithm we are going to look at for parallelization is Prim's algorithm. So how does this algorithm work? So let's see that with an example. So let's consider a simple graph. So this is the graph. I have a vertex A, B, C, then a vertex D, and let's connect it this way, and another vertex E. This is my graph. Okay, and let me put some weights on this. So 1, 1, 2, 5, 3, 3. All right, these are the weights. Okay, so how does Prim's algorithm proceed? So what it does is, so it starts with some vertex. Okay, so let's call that the root. Okay, root is some vertex from which the algorithm is going to start, right? So every vertex is eventually going to be included. So it's all right if you start with any vertex, right? Okay. What it does is it maintains this tree, a set, which is eventually going to be our tree, right? Let's just call it T because it is going to be our tree at the end of the day. So let's call the root R, right? So initially it initializes this tree with the root R. So for this example, right, let me take the root to be B. So initially it starts with the tree as just containing the vertex B, right? And now what it does is it examines all the new vertices which are reachable from the set T. Well, for now, since B is the only vertex in the set T, it basically looks at all the edges from B. Okay. So what are these edges? These are BA, BC, and BD. Okay. And now what it's going to do is it's going to maintain an array D. This array D basically keeps track of the distances from the current set T to all the new vertices. Okay. So this is going to basically have an entry for every vertex. So I have A, B, C, D, E, right? So what's the entry for B going to look like? B is already in the tree T, right? So the distance to B is 0. That's where I'm starting from. The distance to B is 0. Now let's look at all the vertices which are outside of T and see what is the distance to them, right? So the distance from T, from the set T to the vertex A, you have an edge of distance 1, right? Which is the edge BA. Yeah. Similarly to C, you have a distance of 5, and to D, you have a distance of 1. And what about E? Well, E is currently not directly reachable from the vertex at T. So we are only looking at direct edges. Okay. So not paths leading to the vertices. So if I directly look at the immediate edges going out of the set T, E is not reachable. So I initialize E to be infinity. Okay. Now what Prim's algorithm does is it picks one of these edges which has the minimum distance. Okay. So of the edges going out of T, which is the one which has minimum distance, right? It's either A or D. Yeah. So it can pick either of them. So let's say we pick the edge B, comma D. Right? So we pick the edge BD. And what does that mean? So what I'm going to do now is I'm going to add the vertex D to the set T. So what is my set T now? So T becomes, well, earlier it had B, now D is also there. All right. Now I'm going to go to the next iteration and I have to update my D values, the shortest distances from the set T to the vertices. So let's see what happens over here, right? So again, I'm going to have an entry for every vertex, right? B is already frozen and D I've already added to T. Well, I don't really care much about this entry D now, right? The important thing to keep track of is that the edges which are being added. So BD has been added. I'm not going to bother too much about what this value is. So let's leave it to the last D value that was there when we included it, right? So that is 1. Okay, so this value won't change from now on. All right. So now we have to update the remaining entries. So now what happens is this, let's call this the frontier. This frontier changes. And now the new frontier is going to look something like this, right? This is the cut. By frontier, I mean the cut, right? The cut which separates the nodes in T from the rest of the nodes. Okay. Yeah, can I now update the array D? So what will be the new value of A? What is the shortest distance from the set T to the vertex A?
It remains the same.
It remains the same. It's 1. What about C?
It changes to 2.
It changes to 2, right? So this is where a change has occurred, right? And what about E?
It remains infinite.
All right. So what has happened at this step essentially is that you've discovered a new edge which has a shorter distance to reach C than any of the edges before, right? From the set T. Okay. So I now repeat the same process. So what do I do next? Well, which one do I pick now? Well, the minimum edge is the edge to A, right? The edge BA. So I have to pick BA. Okay. So let me just mark what I've picked. So I've already picked this, right? And now I'm going to pick BA. And what do I do? Well, I add this new vertex to the set T. So my spanning tree has just expanded and it now contains the vertex A as well. Yeah. So let me go to the next iteration. So I again look at the values of D and I update them. Right. B was already frozen to value 0. D was frozen to value 1. And now we have frozen A to value 1. Right. Now, what's the shortest distance to C? That remains 2. Sorry. So to update, let me just change my cut. So this is what my new cut is going to look like. Yeah. So what changes? C remains the same. The shortest edge to C is 2, right?
E becomes 3.
E becomes 3. So that's the new change that has developed. Okay, what do I do next? Well, I pick, which one am I going to pick? I'm going to pick C, obviously, right? That has the shortest distance. So I freeze this. So I basically pick DC, include it in my spanning tree, and my tree now extends to B, D, A, and C, right? And then in the next step, the only vertex left is E. So what will the new frontier look like? Okay, so after this, the new frontier will look like this. Well, I didn't tell you what this edge weight is, sorry. So this comes into play now, right? Because the distance to E in the next iteration is going to be the minimum of these two, right? So let's take this to be 5, okay? So that doesn't change anything. So in the next iteration, so 1, 0, 2, 1, and now I have to look at what is the distance to E, and the distance to E remains to be 3. So I'm going to just add this. So I'm going to pick the edge AE, right? Pick AE, add it to the spanning tree, and now I have all the vertices covered, right? I'll just write V of G. This is the new edge that has just been added to the spanning tree. Okay, so the green is basically my spanning tree. Well, it just turned out to be linear in this case, but it can be whatever structure, right? It has to be a tree. Then I'm done with the algorithm because I've already covered all the vertices. So I have a spanning tree. Okay, so any questions on this?